Hi everyone, today we're going to look at standardization, so how to change a normal distribution into a standard normal curve, and we're also going to look at something called the 68, 95, 99.7% rule, and this will give us a way to solve problems related to the normal distribution in exam 1 when we don't have technology. So to start with, if we consider the spread of data, so here we have a normal distribution. And for any normally distributed random variable, approximately 68% of the values lie within one standard deviation of the mean. So that's what we have represented down the bottom. Remember, this Greek letter mu represents the mean, and this Greek letter sigma represents the standard deviation. So we have here that if I was to go from the mean and add one standard deviation and subtract one standard deviation, we will always end up with 60% of the values within that range. Another way that we can write this is that the probability that any value x is between the mean minus one standard deviation and the mean plus standard deviation will be equal to 0.68. We say approximately equal to because this is a rounded off decimal value. Similarly, if I was to now look two standard deviations from the mean, if I was to take the mean and add two standard deviations, or take the mean and subtract two standard deviations, within that set of data we get 95% of all possible values. So 95% of all values lie within two standard deviations of the mean. And so the other way we can write this is the probability that any value x is within two standard deviations of the mean is approximately equal to 0.95. Finally, doing in the same way, we have if we were within three standard deviations of the mean, we end up with 99.7% of all data values are within 3% of the mean. This means that it's extremely unlikely to have a piece of data which is more than 3 standard deviations away from the mean. And so again, we can represent this as a probability as well. Now, these percentages, 68%, 95%, 99.7%, you will need to know them to help you solve problems in exam 1, and they are not on the formula sheet. So those are values to remember, 68, 95, 99.7. Sometimes the exam 1 questions might have clues to help you if you've forgotten those, but better to remember them just in case. Let's look at how we can use those to solve some. So here we say the heights of Year 12 girls at MGSE were found to be normally distributed with a mean of 164 centimetres and a standard deviation of 4 centimetres. I want to determine the approximate percentage of girls with heights between these values. Now when you get these questions, I strongly recommend you draw a diagram. Diagrams are acceptable method marks, and it also helps you visualize what's going on. So here's my normal distribution, doesn't matter if it's not perfect. The mean in the center is at 164. If I was to go one standard deviation from the mean, I would get to 168, and then I would get to 160, one standard deviation that way. If I was to go another standard deviation, add on an extra 4, I'll get to 172, or subtract 4, I'd get to 156. If I was to go once more, I would get to 176 or to 152. Now, if we consider the particular question that we're asked, in this case, I want heights between 160 and 178. That means I'm looking for this amount here. And here, this is within one standard deviation of the mean. I have the mean, I've gone one standard deviation to the left and one standard deviation to the right. And remember, that the chance that any piece of data is within one standard deviation of the mean is equal to 68%. So we can write that as the probability that 160 is less than x is less than 168 is equal to 0.68 or 68%. Heights above 172. So if I was looking above 172, that means if I was copying this same picture here, here's my mean at 164. Above 172 means I'm looking for this part here. Now, here's my mean. 1 standard deviation I get to 168, 2 standard deviations there. Remember that we know, that within 2 standard deviations, so between 156 to 172, within 2 standard deviations here, we have 95% of all data values. That means that in these extra bits on the side, those 2 extra bits together need to add up to 5%. 95% within 2 standard deviations, so on the either end, that's going to add up to 5%, so I'm going to have 2.5% here and 2.5% here. So our probability that our heights are greater than 172 is going to equal to 2.5% or 0.025 as a decimal. So we're using the diagram to help us figure this out. Finally, we want heights below 152 centimeters. So same idea. We have our normal distribution. We have our mean at 164. 152 is 3 standard deviations away. So we've gone 160, 156 to 152. We're 3 standard deviations away. And we also know that within 3 standard deviations, I've got 99.7% of the data. That means in these little extra bits on either side, that's going to have to add up to 0.3. So what I'm doing is that I'm taking 0.3 and dividing by 2. So 99.7 is where we were up to, and then dividing 0.3 by 2. So if we're doing our 0.3 divided by 2, we would get 0.15. So the probability that x is below 152 is equal to, that's the percentage as well, 0.3% left on either side, so 0.15% or 0.0015. So very, very unlikely. Now, the other thing we can do with our probability, our normal probability distributions, is that we can write these as a standardized value. So to convert to standardized values, we've got a particular formula that we can use. This means that I'm changing something to a standard normal distribution. Remember that for a standard normal distribution, the mean is equal to 0 and the standard deviation is equal to 1. So this is our formula. We always use Z to represent the standard normal distribution. So whenever you see Z, it's referring to the standard normal. What we do is we take our previous x value, we subtract the mean and divide by the standard deviation, and that gives us a standardized value. The standardized values can be positive or negative because in our standard normal distribution, the mean is at 0. So we get negative values to the left and positive values to the right. And once we've standardized, we can use these to compare 2 different distributions. It's hard to compare when we've got different means and standard deviations. Once we've standardized, then we can compare any 2 different sets of data. So as a possible exam question here, this was in exam 2. We've got a continuous random variable has a normal distribution with mean of 14 and standard deviation of 2. If the random variable z has the standard normal distribution, then the probability that x is greater than 17 is equal to. So if we draw a picture to think about what's going on, so we've got our normal distribution, we've got a mean of 14 and a standard deviation of 2. So we go 2 on either side, that's 1 standard deviation. If I was to go again, I'd get to 18 and 10. And I'm wanting to look at the probability that x is greater than 17, which means I'm looking here. And at this value here, I have gone 1.5 standard deviations from the mean. The other way that we can get that value is that if I was to standardize, my formula to standardize is that I take x, I subtract the mean and divide by standard deviation. X is 17 minus the mean is 14 divided by the standard deviation, which is 2. That will give us 3 over 2 or 1.5. So we're saying that value is the same as in the standard normal distribution, sorry about my bad drawing there, mean of 0, value of 1.5, and these probabilities are the same. So that means the probability that x is greater than 17, this area under here is the same as this area under here. It's the same as the probability z is greater than 1.5. Now, unfortunately, when we look, none of those options are there. However, because the normal distribution is symmetrical, that means that this purple area here is actually exactly the same as this yellow area here. Because it is symmetrical, if I go 1.5 standard deviations from the mean in either direction, I will get the same area under the curve, which means the same probability. So another way, an equivalent way of finding this probability is by doing the probability, the probability that z is less than negative 1.5, which gives us the answer D. So do keep in mind that the normal distribution is symmetrical, as this gives us some other ways to determine exactly what's going on. Let's look at our last example for today. So this was in exam 1, no calculator, no notes, no formulas. We have a random normal distribution is normally distributed with a mean of 2.5 and a standard deviation of 0.3, and z is our standard normal distribution. We want to find the value of b so that these two probabilities are equal. So if I was thinking about this for my original graph, I've got a mean of 2.5 and a standard deviation of 0.3. If I add on 0.3 once, I'll get to 2.8. If I add on it again, I'll get to 3.1. So if I've gone 2 standard deviations over, that's the part that I'm looking at. If I was to convert that to a z value, a standard normal value, I'm doing my x value, which is 3.1, minus the mean, 2.5, divided by the standard deviation, which is 0.3. 3.1 minus 2.5 is 0.6, divided by 0.3. That's the same as 6 divided by 3, which will give an answer of 2. So what we're saying is that this is exactly the same as z greater than 2. So in my standard normal distribution, my value of 2, that's going to be the same as the probability z is greater than 2. But I want z less than a number, which means I need to find the symmetrical part over here. And so what I will be looking for is the probability z is less than -2, which means that the value of b is equal to -2. Part B, using the fact that correct to 2 decimal places, probability z is less than -1 equals 0.16. Now what we're doing here is a conditional probability. Because we've got some information about standard normal, and because standard normal might help, although we could do it without as well, if I wanted to, I can convert this to standard normal values to start with. So if I'm converting each of these, z is going to be equal to 2.8 minus the mean divided by the standard deviation. So 2.8 minus 2.5 is 0.3. 0.3 divided by 0.3 is 1. And the second one there, z equals 2.5. Well, this one is going to just give me 0. 2.5 minus 2.5 divided by 0.3, that's just going to be 0. If we're setting this up, we've got probability z is less than 1 given z is greater than 0. So conditional probability, in the numerator I want both of these to be true. So if I'm trying to think of a situation, here's my mean of 0, where z is less than 1, here's the 1 value here, and z is greater than 0, I'm going to be looking at just this section in here. So the numerator is where these two things intersect, which is going to be where z is between 0 and 1. And the denominator is the thing we've been given, which is that z is greater than 0. To find the numerator here, I want this part in here. I know that within 2 standard deviations, it's equal to 68%. So half of this is going to be 34%. So I will get 0.34 divided by the probability z is greater than 0. 0 is the mean. We've got half a chance of something being greater than the mean. So this means we will get, if I multiply numerator and denominator by 100, I'll get 34 over 50, and we can simplify this to give us 17 over 25. Now, if you couldn't remember that 68% rule, that's how you could have used this. Because you know z less than -1 is 16, that means I know that this here is 16%. If I know that's 16%, that tells me this one has to be 16%, and from there, because it all adds to 100, I can work out the area I was looking for. So once again, something to make sure you're remembering for exam 1 is that rule 68, 95, 99.7%. Have a go with these questions, and as always, let me know if you have any questions. Thanks everyone.